Hello and welcome. Today's topic, we're going to learn that the wonderful thing about op amps is that op amps are wonderful things. And we'll talk about how they operate. We'll go through the golden rules, which are very important and something you want to know because they make an analysis of op amp related circuits so much easier. And if I just happen to be a student in this class, I'd probably want to know very much how to use these rules and apply them and be comfortable doing it, just in case a question were to come up on the next exam where somebody gave you a drawing of a op-amp circuit and asked you to figure out what it did. I hope I'm not being too subtle here, am I? Okay, so let's move on. Op-amps, what are they? Where'd that name op-amp come from, Well, if we go way back in time to the 1600s, back before electricity had been invented, back when people had to watch TV by candlelight, it turns out that that's when the word computer came into being and became common. You could get a job as a person doing computation, sitting down with pencil and paper and just doing the math, cranking out answers to questions, and earn a decent living as a computer. A little later in history, people started developing mechanical computers. Those work, but they're kind of clunky, literally. And then in the 1950s, the analog electronics computer came along, and that's a picture of one on your screen there. And the idea of an analog computer was you would build circuits that would do mathematical operations. You would add, subtract, multiply, divide, integrate, differentiate, calculate logarithms, and all that fun stuff using basic circuits. But of course, to program one, you don't want to have to design a new circuit and wire up a new circuit for every single potential mathematical operation. So somebody came up with the idea of the operational amplifier, and that's actually these tubes up here are all op-amp tubes. And the operational amplifier was the heart of a circuit that you could create by using jumper wires from one point to another and inserting and jumping the circuit down to variable resistors and capacitors and things, and just insert jumper wires here, there, willy-nilly. I'm just drawing to random places to connect up these resistors, variable resistors, and you can plug in capacitors and things. And just by connecting resistors and capacitors around these op-amps up here, you could create circuits that will do mathematical operations, hence the name operational amplifier or op-amp. Since the days of vacuum tubes, these have become much more common. The LM741 is a very common op-amp, and I can normally even remember that number. It's so common. So if a mechanical engineer can remember the number of a chip, it must be fairly common, right? So they're all solid state now, and they have some very nice properties that even though we don't commonly use those analog computers anymore, they're just handy-dandy devices. So we're burning daylight. Let's move on. An op-amp is basically a difference amplifier. You have two inputs here, an inverting and a non-inverting. And if the positive or non-inverting input is greater than the negative one, the output is driven in the positive direction. If the negative input is greater than the positive input, the output is driven in the negative direction. Okay? That's pretty simple. And so basically our output voltage is some gain times the difference between those two inputs. And that's kind of a graph here. Let me finish getting all of the animation. There we go. This is a practical op-amp. It has a positive voltage input, a negative voltage input, and those define the limits at which it saturates. You can't output a voltage higher or lower than the power supply that you're given, and these limits are commonly referred to as rails. So if you're banging against the rails, you're hitting the limits of the circuit based on the power supply that you have. And there's a couple other inputs here where you can trim to compensate for any manufacturing variations. But normally, and here's what it looks like sitting on a chip, that's 741 op-amp pinout. But normally when we're drawing it for this class and in simple circuits, we'll ignore a lot of those details and we'll just draw it using this triangle, which is the symbol for an operational amp. The negative input, the positive input, and an output. And we will typically just work with that and assume that the physical limitations don't exist, because we'll make assumptions that we are using an ideal op-amp, which on the next slide. Okay, there we go. Here are the characteristics of an ideal op-amp. And using these characteristics, we can then develop what are commonly referred to as the golden rules that we'll use for analyzing these circuits. The ideal op-amp has an infinite gain. So if there's any difference between the negative and positive inverting and non-inverting inputs, you get an infinite voltage output there, either infinite negative or infinite positive, okay, if we just operated it like that. The reality is that the gain is on the order of 10 to the 4th to 10 to the 6th. That's pretty high. That works pretty good. We assume that the input impedance, the impedance coming in this way, is also infinite. That really simplifies the circuit analysis. The reality is that the input impedance is hundreds of kilo ohms, 300,000 ohms. That would be on the low side, to thousands of gig ohms, especially when you get into CMOS-based op-amps. The assumption is also that it has zero output impedance on the output side, so it can drive anything, right? That's not true, but it's close enough. Typically, you got 150, 200 ohms. They're able to drive reasonable circuits. Bandwidth, we assume it's infinite, so if I give it an exact square wave in, you get an exact square wave out somehow. It's not infinite. I don't have, somewhere in this presentation we'll look at a picture of the frequency response. But for most mechatronic applications, it's good enough. And what it comes down to is, for your particular application, if you have a fairly demanding circuit and you need some fairly high-speed response, you can find an op-amp that will probably do the job. Just have to dig through the data sheets. And ideally, you have zero offset, so if the difference between these two inputs here is in fact equal to zero, you get zero output. They don't quite do that, and then that's why we put the trim ports on there, so you can tweak it a little bit and get it very, very close for practical purposes. Okay. This implies that it's seldom used in open loop mode. Why? Because any difference here gives you infinite output, or certainly very high output, or at least banging against the rails. And what's the point if you're just banging back and forth against the rails? So we always use it in a feedback mode, and we'll get to that on the next slide, because when we use it in that feedback mode, we can apply what are known as the golden rules. The golden rules apply to the op-amp only when the op-amp is operated within its listed specifications. So if you're banging against the rails, if you're applying frequencies that are too high for that op-amp, or voltages that are too big, you can't do this. And they also imply, and this is an important one, when you're in negative feedback. What is negative feedback? It is not just somebody telling you that they hate you. What negative feedback implies, this is our op-amp, we have the inverting and the non-inverting inputs, we have our output, we have some sort of connection between the output and that inverting input. So there's a feedback circuit between the output and the input. It goes back to the negative or inverting input, and we'll put something here and we'll put something here, some resistors, capacitors, something here to design our circuits and make things actually perform the mathematical operations that we want. But the key is you always have this connection from the output back to that inverting input. That's the negative feedback. So if we operate within these limitations here, and we make the assumptions of an ideal op-amp, we can assume that the inputs, let me draw that again, I shouldn't have erased everything, negative, positive, those are my inputs. I'm going to assume that the current into the op-amp is equal to 0. The reality is it draws very little, 0.5 milliamps for the 741. A lot of them draw even less, so I can say that I minus equals 0, I plus equals 0. So I have no current going into this device here, okay? Output, and we're going to have something up here. There's always this negative feedback. So by assuming that there is no current going into the device itself, we don't have to, it just really simplifies our calculations or our analysis. And the other key rule here is that the inverting and non-inverting inputs remain at the same voltage. Whoa, dude, where'd that come from? Basically what it means when you have this feedback loop, if there were any difference between, V minus and V plus, it'll drive V out to infinity if there were no feedback, right? But because there's feedback, we come back here and change, essentially combine the input voltage V in with the output voltage, and there'll be some, passive components there. We'll combine those to change what is seen at this pin until it matches what's at that pin. So those two voltages, these voltages here, V minus equals V plus. And the high gain of that op-amp makes all that possible. So basically, it looks at the input terminals, change the output voltage such that the external feedback network will bring the input difference to 0. So what this means is when I design or analyze my op-amp circuit, I have, even though these pins aren't connected, and say I have that connected to ground, if this is the ground, I know that if V plus equals 0, then V minus equals 0, and the current going into my device is 0. Now all of a sudden, I can take the characteristics of that op-amp out of my analysis. I don't care. I'll come up with an answer for how the circuit works that doesn't actually include the op-amp in any of my math. So, let's move on. We'll apply a very simple application here, as a voltage follower here. We have our positive input here is connected to our input voltage from wherever it comes from. Our output voltage is connected to wherever it goes. And we have just a feedback connected right directly back to the minus input, right? So if I apply the golden rules, I know that E plus equals E minus, right? So this voltage here is going to be equal to V in, and that I plus equals I minus equals 0. There's no current there, okay? And so what's going to happen here? Well, the current one is probably not important for this circuit. Well, V out has to be equal to V in, because if this is equal to V in and it's connected to there, and there it is, because we have driven these two, the op-amp will drive those two pins, or drive the negative pin to be whatever it needs to be, so that V out, or V minus and V plus are the same. We now get V out equals V in, and end of story, So what would be the point of doing this? Remember that the input impedance here, we said was infinite, so my I here is 0. So I have this connected to a circuit. I'm not drawing any current or any power from that circuit. I have that very high input impedance, so I can make measurements of a circuit without affecting that circuit so much. And the output impedance is low, so I can go drive LEDs, I can drive meters, I can drive whatever I need to do on the output side without sucking power out of my input circuit. Okay? So it decouples the output from the input. Simple voltage follower. A little bit more complicated here is our inverting amplifier. Here we've got our positive non-inverting input. It goes to ground. Okay. Here's our input voltage here. We have a resistor input, a resistor in our feedback loop, and this goes to the negative. So we apply our golden rules that E minus equals E plus. So that tells us in this case what is E plus. E plus equals 0, so I can say that E minus, or the voltage at this node right here, is 0, right? And I minus and I plus equals 0, so if the current going in here is equal to 0, then I know that the current coming through here has to equal the current going through there through Kirchhoff's, current law. The current, current is neither created nor destroyed at a node, okay? So that's what I have here. My E plus and my E minus are equal to 0. My input current equals the feedback current plus the current going into the negative, which we know equals 0. So if I apply Ohm's law to the feed forward and feedback, I can say that, and I know that my input current equals my feedback current, so EI and EO, EIO, EI, our input voltage, minus E minus, which is the voltage here at that negative input, which we happen to know is equal to 0 because it's equal to our 0 volts here, divided by the resistance on that input circuit gives us II, which is equal to IF, which is equal to, applying Ohm's law, E minus, which the voltage here at the minus terminal, which again we know that equals to 0, minus E output, our output voltage, divided by this value of this feedback resistor RF, so it's just Ohm's law applied across that resistor. So I can rearrange and simplify, and I get the output voltage over my input voltage equals negative feedback divided by the input resistance, and one more rearrangement, and I get my output voltage, which is what I want, is now the input voltage times the ratio of those two resistors times -1, okay? So I have an equation here for my output that doesn't include the op-amp, okay? There's nothing about the op-amp in that equation. All I have, if I want to figure out what the output voltage is for any given input voltage, all I need to know is the value of those two resistors and the fact that it's inverting, so the answer comes out negative. What could be simpler, right? You can do this on an exam, right? Right? Okay, so basically, as an operational amplifier in a computer, now I'm doing multiplication and division based on the ratio of those two resistors, and if I wanted to make a programmable multiplier, I could fix one of these resistors, put a precision potentiometer in place of the other resistor, and then I just turn that potentiometer up and down to get the multiplication constant I want to use. Non-inverting amplifier, it's kind of inconvenient to have that negative sign there sometimes. So here we connect and we've kind of flipped this symbol for the op-amp upside down. But so this is the inverting input. This is the non-inverting input. And as before, we have our voltage. Well, not as before. We've changed it. Our voltage input is going to the non-inverting input. The inverting input or negative input goes to ground through a resistor. And we have our feedback resistor here. So we can again apply our golden rules where these two voltages are the same. And the current here equals 0, okay? So if I say that, I can say that En equals E plus, right, just because they're directly connected, and that means that E minus is going to be the same as En, and we also know that the input current on the minus leg here, this input current, I'll put a minus there, is equal to the feedback current plus I minus, which is 0. And so this is I. Let me relabel that here just to make it clear. This is IF going that way, and this is I going that way, I minus, okay? So from those two relationships, I can again apply Ohm's law to those two resistors, and I say that E minus, which is also equal to E in, right, minus 0, because it's going to ground, divided by that Ri is my current II minus, which is equal to my feedback current, and the feedback current is the output voltage minus E minus, which again is equal to EI, divided by that feedback resistor. Juggling that around, I get my output voltage is the input voltage times 1 plus the feedback over the input resistor, okay, which actually goes to ground. So again, I have an equation where all I need to know is the ratio of those two resistors, and I can tell you how this circuit behaves and what, for any given input, what the output's going to be. It's got this 1 plus, which isn't quite as neat and convenient as the previous equation, but we also don't have this inversion problem, if it's a problem, okay? What if Rf equals 0 and Ri equals infinity? Well, if Rf was equal to 0 and Ri was equal to infinity, this would be 0, this would be infinity. Oop, that's an 8. Infinity goes sideways, doesn't it? So then that term would pretty much go to 0, I think. And what would be left is E out equals E in, right? That was essentially our voltage follower from a couple slides ago. Simple? Clean? I would expect that, you know, these are very simple examples. In other examples, like if you want to do integrating, differentiating, filtering, things like that, you're going to start putting in capacitors and inductors in one or more of these places, or combinations of resistors. But it's just basically applying these rules and grinding out from Ohm's law or from the, you know, impedance rules for impedance of a capacitor or an inductor. You can come up with algebraically come up with the equation for the output voltage as a function of the input voltage, and we'll go from there. Okay. A couple other practical considerations. 2 to 10 megohms, those are slightly different numbers than we saw before. They're they're high. Output impedance 10 to 100 ohms, gains 10 to the 4th, 10 to the 7th. Operating voltage 1 to 15 volts, and typically we want to supply a plus and minus, say plus and minus, plus 10 and minus 10 volts, so we can get positive and negative outputs from that device. So that's a little bit of an inconvenience, but if in practical operations, if you just had a couple of 9-volt batteries, use my artwork, and this is plus, and this is minus, and this is plus, and this is minus, and I connect these together, connect this to my system ground, this becomes V plus, and this becomes V minus to power my op-amp, and that's the easiest way to make a power supply for these op-amps is just a couple 9-volt batteries, okay? So it's not a, it's not a disaster. Frequency response, I don't know what exact op-amp this is for, but basically, you get much above, looks like about 10 hertz, you start to, the response starts to fall off. So this one isn't very fast, but you can get faster ones. And what's inside an op-amp? A lot of stuff. There's just a lot of stuff in here. And we're not going to go into the details, but basically you start out, there's this differential amplifier on this stuff. Here's the non-inverting input, the inverting input, and then you have two other inputs here, offset null, where you'll adjust those slightly just to get rid of any difference, any output when the two inputs are shorted together. An output amplifier to give us our final gain. There's our output there, and somewhere on this thing we have our positive voltage input and our negative voltage input. And if you kind of look at the way the circuit is drawn here, we have this negative voltage all the way across the bottom, positive voltage all the way across the top. Those are the rails. That's where that term comes from. And any output voltage is basically limited by these plus and minus voltages. So if you try to exceed those, you hit the rails. And that should wrap it up. I would encourage you to look at some more examples and make sure you're comfortable with using these golden rules and more complicated circuits. You can do addition, subtraction, integration. Filtering is essentially an integration process. And till next time, how about some theme music? Happy trails to you until we meet